Hey kiddos, in today's video we're going to talk about Bronsted Lowry acids and bases. If you remember from your Chemistry 1 days or your introductory chem stuff, there were three ways that we could talk about acids. We could have Arrhenius acids, where there were the acids produced hydrogen, the bases produced hydroxide. We could have Lewis acids and bases, where we had electron pair acceptors and electron pair donors. And then we had something in the middle that was Bronsted Lowry acids and bases. Bronsted Lowry acids and bases are really going to be the ones that we're going to use the most in chemistry class. So that's what we're going to talk about today. Make sure that know the definitions, and more to the point, that you can find conjugate acid-base pairs and be able to do some stuff with those. So let's talk real quick about Bronsted Lowry acids and bases. To do that, I'm going to write us an equation up here. Okay, so if we look at this equation, this is an acid-base reaction. And so we've got an acid, we have a base, although that might not seem apparent immediately. And what they're going to turn into are two products on the other end. Remember that we're dealing with reversible reactions here, and we're going to talk a little bit about simple equilibrium in the next video. Don't worry, guys, we're not getting super heavy into the math on it, but you need to know the setup of it. But that just means that this reaction can go forward, it can also go backwards, and that's indeed going to lead us to the next things that we need. And so if I asked you to look at this and say, hey, which of these things is the acid and which of them is the base? So if you don't remember off the top of your head which thing is the acid and which thing is the base, here are Bronsted Lowry definitions. Essentially, a Bronsted Lowry acid is one that donates a proton, it gives up a proton. A Bronsted Lowry base is something that accepts a proton, it brings a proton into itself. And what is absolutely vital here is that you remember that what a proton is a proton is a hydrogen ion. Remember that hydrogen has a proton and electron, normal non-isotopic hydrogen anyway. Proton, electron, no neutrons. If it's a positive charge, it means it's lost the electron, and therefore pretty much all that's left to it is going to be a proton. So that's why we get the proton donor and proton acceptor. Okay, so something up here has to give a hydrogen, something up here is going to accept a hydrogen. If you look at this, you could tell pretty swiftly that this is going to give up its hydrogen because it's by itself on the other side of the equation. That this, the water, is going to accept a hydrogen because it is now H3O plus on the other side. And so we could label these and say this is my acid, water is my base. You might be asking yourself, is water always the base? Nope, sometimes water is an acid. Remember that water is amphoteric. It can be either of those things. And so here's the part that many students forget. So you got proton donor, proton acceptor. This is the acid, this is the base. Let's talk about conjugates. So I could pretty this up and give you some really complicated definitions for what the conjugate acid and conjugate base are. But essentially it comes down to this. The acid turns into the conjugate base. The base turns into the conjugate acid. They're always in an acid-base pair. Okay? It's an acid on one side, it's the conjugate base on the other. It's the base on one side, it's the conjugate acid on the other. And so what I mean by what it becomes is, remember we said that the acid here, we know that it's the acid because it loses a hydrogen. That's what a Bronsted Lowry acid does, right? Loses a hydrogen or donates a proton, however we wanted to put that. Well, so what does that turn into? Well, if we look at that in the equation, that becomes that, right? The HBr turned into a bromide ion. And so what that means is that the bromide ion is my conjugate base. It's what the acid turned into. Okay? Conversely, and you can already sort of fill in the blank, but it's important to be able to look at it and see why it's going that way. The base, okay, what bases do is they gain hydrogens, they accept protons, and in this case it becomes H3O plus, or a hydronium ion. Okay, and so that means that that is my conjugate acid. Okay, and that's really as complicated as it gets. Now, why does that matter? In what world would that even matter? Well, it matters because, remember, reactions are reversible, and I could flip this whole reaction around so that these two things were the reactants and these were the products, okay? And if that happened, then this becomes my acid because it's going to give up a hydrogen to become water. This is going to accept a proton, which means it's going to be the base if we were going in reverse. So that becomes really important the more we talk about these reversible equilibrium scenarios. So let's do another example or two just to make sure that you've got it. And then in the next video, we'll talk a little bit about equilibrium basics and how that feeds into this acid-base thing that we're talking about now. All right, so let's talk a little bit more here about, just do another example here for our Bronsted Lowry acids and bases. So really quickly, let's decide what's acid, what's base, what's conjugate, and all that. And then we'll talk about a couple other things really quickly. So my ammonia here becomes ammonium, and it does that by it gaining a hydrogen, it gaining a proton. And so that means that this has to be my base in this case. And so what it turns into is the conjugate acid. The base becomes the conjugate acid by gaining a hydrogen. The acid in this case is water, and again I said in the last example that even though water was the base in that one, it doesn't always have to be. So water is the acid in this case. I know that it is the acid because it loses a proton, it donates a proton, and it becomes OH minus. And so therefore that is my conjugate base. So now we've got our pairs, base, conjugate acid, acid, conjugate base. What also is really important for us to note here is that much like our curved arrows in resonance, we're going to draw curved arrows to show how things are happening here in our conjugate acid-base pair. So we want to see where things are going to, where the electron's going. So in this case, I'm going to say that my electron pair here, or I could say my region of electron density, is going to leave the bond between the hydrogen and the oxygen, and it's going to form a lone pair on this oxygen over here, which is obviously going to give this a formal charge of -1. And then at the same time, my lone pair here on my ammonia is going to bond to the hydrogen. It's going to give me this hydrogen over here. Bonding that hydrogen there, of course, will take my nitrogen and give it a positive formal charge as well. Here's what's really important, and an important distinction between resonance and what we're doing here is that in resonance we said that the electrons weren't actually moving. We're just sort of, again, trying to represent in an incomplete way what's really going on in resonance. In an acid-base scenario, this actually does represent the areas of electron density moving from place to place because we're reforming some bonds here. Okay, so some bonds are getting reformed here, and so that's pretty important that we're getting that drawn out correctly. So bond there, that gives me this bond. That becomes one of the lone pairs back on that hydroxide that is our conjugate base. What is also important here real quick is I'm going to write down a couple of things that I think are really important for you to know. So one last really quick thing here is that it's really important for us to know, and we're going to dive into this a little bit more in the equilibrium video and talk about Ka values and all that, but the stronger the acid or the base, the weaker its conjugate is going to be, and conversely, the weaker the acid and base, the stronger its conjugate is going to be. So for instance, this ammonia is a relatively weak base, and so that's going to mean that its conjugate acid is going to be a little bit stronger than we might assume in some other situations. If we went back and looked at the previous equation that we'd drawn and we had HBr, hydrobromic acid, that is a strong acid, and therefore its conjugate, which was the bromide ion, that bromide ion is therefore going to be weak because it was a really strong acid base, and therefore the conjugate is weak. Why does that matter? Well, that's going to matter a lot when we're trying to figure out which way the equilibrium shift is going on, and that is going to be our topic for our next video. So hopefully you know how to do conjugate acids and bases in the Bronsted Lowry system, can identify them, and also can draw the curved arrows to represent where the electron density is moving. Thanks, kiddos.